Good morning. Today we're going to start talking about Chapter 8, which is entitled Hypothesis Testing. You may recall from our last class, we're going to start out in Chapter 8 testing claims about proportions, or testing hypotheses about population proportions. And that's the title of Section 8.3. Let me write that down. Section 8.3 is testing claims, or actually they say testing a claim about a proportion, meaning a population proportion regarding some characteristic of interest. Alright, remember from class, a hypothesis is not an educated guess. An hypothesis, at least in the statistical sense, is a claim. A claim about anything, a claim about a mean, a claim about a standard deviation, a claim about, well, in 8.3 it's going to be claims about population proportions. So very simply, a hypothesis is a claim. Basically what we're going to do in this section 8.3, we're going to start out considering populations, and in particular population proportions with some characteristic of interest. You'll recall our symbol for population proportion is little p, and of course we never really know what little p is. Basically what we're going to do is take a sample and based on data from a sample proportion we will test hypotheses or claims about population proportions. So here's what we're going to do. We're going to use p hat to test claims about little p. That's in section excuse me, that's in section 8.3. Okay, we've got to get some terminology down, and before we dig in and do some examples, H0, cap H0 is what we call the null hypothesis. H1, by convention, is called the alternative hypothesis. And in section 8.3 they're going to be claims about population proportion. What we do in wide strokes is we test the null hypothesis against the alternative hypothesis via, well, actually it's via z-scores. So remember that when you're trying to decide which operator to use on your calculator. We'll show you what I mean in a minute. Basically, we're basing this test on z-scores of population proportions, or really sample proportions, via z-scores of sample data. And in section 8.3 it's going to be a sample proportion. And in this section, really throughout all of chapter 8, we're going to use the p-value approach. Alright, so p-value is king. P-value is going to tell it all, and the good thing is the calculator, not surprisingly, will compute the p-value for us once we enter in some sample data. Alright. Again, let me give you some idea where we're going here before we go to the calculator. Basically, my sample proportion will be converted to a z-score. Alright. And your z-score, let's say for example, let's say I get a z-score of my sample proportion, and it ends up here, for example. This z-score will determine a extreme right area in this diagram, and this area is called the p-value. Well, it's easy to see that extreme z-scores lead to small p-values. Alright, let me write that down. If the sample data is extreme, with regard to the null hypothesis, that means your p-value is going to be small. Your tail area determined by that z-score will indeed be small. Right? And if your p-value is small, then that suggests, doesn't prove, but suggests that h0 is false. There's a problem with h0. It may be false based on this extreme sample data. All right, by convention, your conclusions to hypothesis testing or tests will be one of the following. You'll either, one, reject h0, reject your null hypothesis, meaning your sample data is extreme and data is statistically significant, or you will fail to reject h0, meaning your sample data is weak. All right. Again, and kind of a rule of thumb here, I'll write it down like this. Small p-values suggest h0 is false. And in that case, we will reject h0. And conversely, large p-values will suggest h sub 0, the null hypothesis, is true. And in that case, we'll say the evidence is weak and we fail to reject h0. Sorry about squeezing that in there. Alright, so I'm going to dig right in and get to an example here. And show you how we use the calculator to actually compute p-values. Alright, let me say somebody makes a claim. Remember, an hypothesis is a claim. A claim is made that the population proportion, forgive my abbreviations, of green-eyed people is 0.09. Okay, somebody makes that claim. Alright, so we're going to put that claim to the test. So we're going to do that with a sample and consider a sample proportion. A sample of 500 people gives 55 with green eyes. Okay? Well, that means my sample proportion of green-eyed people is 55 over 500, which is 0.11. Alright, so what we're going to do is test the claim. Test hypotheses, test claims. Test the claim that the population proportion of green-eyed people is greater than the original claim of 0.09. Okay? So in wide strokes, somebody makes this claim that little p equals 0.09. We take a sample of 500. We get a proportion, a sample proportion of 0.11. And we're going to test the claim that this claim may be, we're going to test this null claim, this original claim, that little p equals 0.09 based on data from the sample proportion. Alright. To test hypotheses, the book goes through this, I think it's like 10-step procedure. I claim you can do it in as few as 3 steps, bypassing all the fluff. Step 1 in any hypothesis test is to state the hypotheses. Now we got to be a little bit careful about this. Hypotheses. H0 is what we call the null hypothesis. It's like the king of the hill. It's like the assumed or historically shown value. Right? H sub 0 is always the null hypothesis, and here that is the original claim that the population proportion of green-eyed people is 0.09 or 9%. Right, by convention, the null hypothesis always contains equality. Null hypothesis is always an equals statement. Okay, and that's by convention, by agreement. Alright, so we're going to test this claim with the alternative claim that H1, well, is always the alternative hypothesis and that claim here is that little p is greater than 0.09, as you could see in the above screen. Can I go back? Yes, test the claim that the population proportion of green-eyed is greater than 0.09. Right? Now, the alternative claim is always an inequality statement. And let me write that down. It's always a greater than statement, or a less than statement, or a not equal to statement. Alright, if the alternative hypothesis is a greater than statement, we call this a right-tailed test, for obvious reasons. Okay? Alright. So step 1, state the hypotheses. Let me do it again here. Here is the null claim that little p in this example is 0.09, and H1, the alternative claim, is that little p is greater than 0.09. Which of these claims is going to win the battle? Well, we'll see. Alright, so that's step 1, state the hypotheses. Step 2, find the p-value. Alright, now remember, the p-value is the tail area under the standard normal curve determined by the z-score of p hat. Now, the good news is the calculator will compute this for us. As we mentioned before, calculator computes this. So we're going to take full advantage of our calculator in computing the p-value. It's pretty simple. If you go to your TI 83 or 84, you hit your stat button, we'll hit the test button, and now we're going to use a new operator here. Well, you'll remember in chapter 7 we use one prop z int in computing confidence intervals. Here we're going to use one prop, meaning proportion, one proportion z test. One prop for one proportion, z because we're basing our p-value on a z-score, and test because we are testing hypotheses. Alright, familiarize yourself with the screen here. The first thing the calculator prompts us for is P0. That's the TI code for the null hypothesis. They're really asking us, what does H0 claim about this proportion? Well, it claims that little p is 0.09. So that's our TI code for H sub 0, little p equals 0.09. Okay. The next thing the calculator prompts us for is a x value. Well, x is going to be, well, here it's 55. We had 55 green-eyed people in this sample. So let me write that down. This is the raw count of green-eyed people in the sample of 500, right? That's somewhat similar to the one prop z interval command. Little n, of course, is your sample size, 500. And something new here, they prompt us for, well, they call it prop. And they give us really 3 choices. And this is where we enter in what type of test, what type of hypothesis test we're working on, either a left-tailed, right-tailed, or a two-tailed test. Well, of course, as we said before, the sign in H sub 1, the alternative of hypothesis, determines the type of test. So the sign, the algebraic sign in H sub 1 determines the type of test you're talking about. Well, two-tailed, left-tailed, or right-tailed. So in this case, where you got a right-tailed test, so highlight greater than p sub 0, and of course, then we'll want to calculate. So highlight and select the calculate command, and we'll get a results screen, which I will have to get to a new layer to expose. Hang on a minute. Delete current layer. Alright. Alright, let's go to the results screen. We're still in step 2, finding the p-value. Well, it reminds you of what operator you're using here. It prints out or reveals or shows the alternative claim, just in case you forgot. And again, that's the TI code for the alternative hypothesis. It returns you a z-score, and remember, in this case, in this section, it's the z-score of your p hat value, and gives you a little p of 0.059. Alright, there's an error. There's a copy error here. Hang on a minute. Let me adjust that z value. I thought that looked a little weird. That z value, that z score is 1.56 and change. Alright. And the p value, little p, well, actually that should be a cap p on the calculator, but apparently TI doesn't have that capability. I'll put big stars around this because this is what I want. This is the p-value. This is going to determine whether we reject or fail to reject H0. Alright, my calculator says 0.05906, etc. Alright, so p hat is 0.11, but we knew that, and of course little n is 500, right? Kind of towards the bottom of the screen there. Alright, the p-value is the big determiner here. Okay? Alright, so step 2 is done. We found the p-value for this hypothesis test. Now, step 3. Compare the p-value and make a conclusion about whether to reject or fail to reject H sub 0. Your answers are always going to be in terms of H0, and again, that's by convention in the statistical universe. Well, compare p-value. Compare p-value to what? compare p-value to what we call the significance level. Now this is typically given to you in the problem statement. Its typical values are 0.01, 0.05, and 0.10, kind of small, medium, large levels of significance. And it's what one might consider a burden of proof, the height of the hurdle the evidence has to overcome in order to reject H0. Well, let's see. We compare the p-value to the significance level. In this problem, let's see, I've deleted the screen with all the given data, so let's choose a significance level of 0.05. I think that's the most common one the book uses, kind of a moderate level of significance, and your significance level is symbolized by alpha. Determines just how significant your sample data is. And what I do is I make a little mini table here. I'll compare my p-value to alpha. Well, the p-value we computed, or the calculator computed, was, I'll call it 0.059. Right? If we have a significance level of 0.05, we can clearly see that the p-value is bigger than alpha. Now remember, small p-values suggest H0 is false. Large p-values suggest H0 is true. And of course you're going to ask how large, and the idea is larger than alpha. Right? If your p-value is larger than your alpha level, you will fail to reject H0. Alright, so my conclusion here is fail to reject H0. Let me write down that little blurb again. Small p-values suggest H0 is false. Large p-values, how large? Larger than alpha, suggest H0 is true. Right? So if I've got a large p-value, larger than alpha p-value, my statistical data is weak, my sample data is weak, too weak to warrant rejecting of H0. So, alright, so that's step 3, our conclusion and comparison of p-value. So I'm going to add what I call an interpretive statement. The sample data, and there's a lot of different ways to say this, the sample data or the sample proportion data is not statistically significant enough to warrant rejection of H0. So I have not overcome the burden of proof. I have not overcome the hurdle, the height of the hurdle that I needed to reject H0. Okay? Alright, so that is an example of a right-tailed test of proportion, right-tailed hypothesis test regarding population proportions. Alright, now I want to do a left-tailed test. And as you might imagine, the basic framework is the same. I want to look at number 12 on page 421. You might want to pause there and get familiar with the problem. I'll read it here. Number 12 on page 421. Screening for marijuana usage. The company drug test success provides a one-panel THC test for marijuana usage among 300 tested subjects. So I'm going to start writing down some of this given information right away. Results from 27 subjects. All right, so I'm going to have 27 is going to be our raw count. 27 subjects were wrong, or results from 27 subjects were wrong, either a false positive or a false negative. Use a 0.05 level of significance. All right, so our alpha level, our burden of proof, is going to be set at 0.05. To test the claim, the bells should go off. Test the claim that less than 10% of the test results are wrong. Less than 10%. So really that claim is saying that the population proportion of wrong tests is less than 10%, or 0.1. All right, by agreement, this is going to be the alternative hypothesis. Now remember, the alternative hypothesis always has an inequality statement, either greater than, less than, or not equal to. All right, so clearly we are in the less than case here, so this is going to be a left-tailed test, or a left-tailed hypothesis test. All right. Well, if H1 is the claim that P is less than 0.1, H0 is left for us to figure out. Well, remember, H0 is always the equivalent, well, not equivalent, but the corresponding equality statement. Remember, H0, the null hypothesis, always is an equality statement. Okay? So, step 1, already done. State the hypotheses. Nice and formal. H0, little p is 0.1. H sub 1, little p is less than 0.1. Okay? All right. Step 2 now. We want to compute the p-value. Our p-value is based on our sample data. So I'm going to have to plug these values in to my calculator and grind out the p-value. So let me write down step 2 here. Compute p-value. And again, we will go to the stat command, tests, and again in this section we're going to be concerned with one proportion z-tests. One proportion because we're considering the claim about one proportion, z because we're basing our decision on z-scores of sample proportions, and tests because we're doing a hypothesis test here. P sub 0, remember that's the TI code for the null hypothesis, so I'll put 0.1 x, the raw score, or the raw count of number of tests, marijuana tests that were wrong, and that was 27. Little n we're prompted for, of course the sample size is 300, and we have to pick the right type of test for this proportion test, and of course it's a left-tailed test because the sign in the null hypothesis is a less than statement. Write that down, left-tailed test. Alright, so I highlight calculate and then hit enter, and I get the following results screen. Well, again, they spit out the alternative hypothesis statement, just in case you forget what you entered in for the null hypothesis. It gives you a z-score of your sample proportion, and of course this is the important data here, 28185. I don't know how that mark got there. Let me erase it. This is the p-value. It's the tail area determined by the z-score of the sample proportion, computed upstream, thankfully, by the TI-83. Alright, so is this data extreme enough to reject the null claim? Well, we'll see in a minute. Again, we do this by comparing your p-value to your alpha level. The p-value, well, is 0.281 and change. The alpha level, let me look, use a 0.05. They tell us in the book, use a 0.05 significance level. And of course, in this example, your p-value is greater than alpha. And remember, large p-values suggest H0 is true. Let me write that down again. Large p-values doesn't prove. Again, we're basing our decision on data, sample data. All right, so large p-values suggest H0 is true. In other words, we will fail to reject because our p-value is larger than our alpha level. Okay? Fail to reject H0, and probably a good idea to put your level of significance, because a change in your level of significance might change your conclusion. All right, so there's my conclusion for that hypothesis test. Fail to reject H0 at alpha equals 0.05. The book sometimes asks us for interpretive statements. Let me add a little interpretation here. All right, the sample proportion of, let's see, it's about 0.09, wasn't it? The sample proportion of 0.09 is not extreme enough. I like to use the word significant, because most students are comfortable with the phrase statistically significant. Sample proportion of 0.09 is not significant enough to warrant rejection of the null claim that little p is 0.1. Right, sample data wasn't extreme enough. Alright, so there's a left-tailed test. I'm sorry, yes, that was a left-tailed test. We did a first example was a right-tailed test, second example was a left-tailed test, and now we're going to talk about a two-tailed test. Give me a minute here. Alright. I want to look at number 20. Let's see, we wrote this down. Now a two-tailed test. And again, the calculator makes it easy for us, maybe a little bit too easy. This is number 20 on page 422 in your textbook. And you might want to pause and turn there and get familiar with the problem. I'm going to read it over here. Let's see, it's 20, stem cell survey. Adults were randomly selected for a Newsweek poll. They were asked if they favor or oppose using federal tax dollars to fund medical research using stem cells obtained from human embryos. Of those polled, 481 were in favor, 401 were opposed, and 120 were unsure. A politician claims that people don't really understand the stem cell issue, and their responses to such questions are random responses equivalent to a coin toss. Read this next part carefully. Exclude the 120 subjects who said they were unsure, and use a 0.01 significance level to test the claim that the proportion of subjects who respond in favor is equal to 0.5. Alright, I'm going to write down some given. It says excluding the 120 who said they were unsure, use a 0.01 significance level. That's kind of like a high level of proof to test the claim that the proportion, really population proportion, of subjects who respond in favor is equal to 0.5. Proportion equal to 0.5. Alright. By implication, this is H0. Right? H0 is always an equality statement. An equality statement, okay? Well, it doesn't tell us directly what H1 is, but if they claim H0 is the statement P equals 0.5, well, that means we have to allow for being either high or low. So I'll write down H1 is the statement or the claim P is not equal to 0.5. Remember, H1 is always either a less than, greater than, or not equal to statement. And by implication here, it's a not equal to statement, and if your H1 sign is not equal to, then we have what we call a two-tailed hypothesis test. Alright. Let me rewrite this. I'm going to say step 1, state hypotheses. H0 is the claim that the population proportion of those in favor are half. And then H1 is that the population proportion of those those in favor is not 1/2. And step 1 is done. Alright, we've done this at least twice before, so now step 2, we can compute the p-value. And again, we enter here, hit stat, select the test submenu, and the one proportion z-test command, and the calculator prompts us for some things. Well, for P0, P sub 0, remember that's the TI code for the null hypothesis. Alright, now I have to think for a minute. X, they want the raw count of those in favor. And they tell us to ignore the 120 that we're unsure. So it tells us explicitly the raw count for those in favor is 481. Now it prompts us for an N, a sample size. Well, if we ignore the 120 who are unsure, I have to add 481 to 401, and I get 882. Alright? So be sure you understand that. This is the sum of those in favor plus the sum of those not in favor. 401. 882. And now in the last, I have to select the type of test. So highlight and select not equal to P sub 0 because we are talking about a two-tailed test here. Okay. So I punch this out and I get a p-value of 0.00706 and change. Let's put ... Remember, well, the calculator, let me write it down the way the calculator gives it to us. Unfortunately, they use a little p. But it's a big implication here. This is your p-value. So I always make a big deal about this. I usually draw a big P with a serif on the bottom, if you like, as long as you make it clear. I don't care how you label it. Alright, so step 2 is done. We've computed the p-value. Now step 3, and again I'll make a little mini table here. I'll compare the p-value to alpha. The p-value is 0.00706. The alpha level, well, if you read the problem, it says use a 0.01 level of significance or significance level. Right? And of course, your p-value is less than alpha here. Now remember, small p-values suggest H0 is false. If you got a small p-value, your z-score is extreme, your data value is extreme, your sample data is extreme, and hence you might think something is wrong with the null assumption, the assumption that the null claim is true. Small p-values suggest H0 is false. How small? Smaller than alpha. So my conclusion here is to, let me write it up here, is to reject H0 at alpha equals 0.01. So this is my conclusion. Reject H0. Alright, so if I add an interpretive statement, I may say something like this. Your sample proportion data is significant enough to warrant rejection of the null claim or null hypothesis. And what was the null claim? That H0 was that little p equals a half, right? Alright, so we've done 3 examples, left tail test, right tail test, and two tail test. I think that's enough to get you going on your homework. We're approaching the 42-minute point, and we'll call it a day. This concludes online class 8.3 for Math 125.